We have studied about the Aufbau principle, which tells about the sequence in which the subshells will be filled with the electrons. The next rule that we will see is the Hund's rule of maximum multiplicity. So, Hund's rule of maximum multiplicity. So, what does this rule states? This states that pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got at least one electron each, that is singly occupied. So, what does this rule states? Suppose we have 3 orbitals in a subshell. So, as long as all of the 3 orbitals do not get 1 electron each, we cannot pair up the electrons. That is, at first all the orbitals will get one single electron. Then if the extra electrons are left which are to be filled in that subshell, then we will go for pairing. Okay. So, for S subshell has one orbital. So, first one electron will go, then another. But for P, what happens? There are 3 orbitals, right? So, if we have to write 2 electrons, we can write like this, and we can also write like this. Which one is correct? So, Hund's rule says this one is correct and this one is wrong. We cannot pair up the electrons as long as there are vacant orbitals left in this subshell. So, pairing cannot occur as long as vacant orbitals are left in the subshell. Okay. Since there are 2 vacant orbitals, we cannot pair the electrons like this. Now, if there are 3 electrons, for 3 electrons, we cannot write like this. This is again wrong. Why? Because after filling 2 electrons, there is still one vacant orbital left. So, we will have to fill up that vacant orbital like this. This is the correct. Now, if we say 4 electrons in the P subshell, now what happens? We have written 3 electrons, 1 in each of the orbitals. Now, we have 1 more electron left. Now, we can do pairing. but we cannot write like this. We cannot write like this. We can write like this. When all the orbitals get at least one electron, then we will pair. So, this is the Hund's rule of maximum multiplicity. So, how long can we go? For p orbital or p subshell, there are 3 orbitals. So, the maximum configuration with singly occupied orbitals can be p3. So, this is called half field configuration. So, half field configuration is when all orbitals of the subshell are having 1 electrons each. So, all orbitals in a subshell has 1 electron each. We call this half field configuration. And since p orbital has the maximum capability of 6 electrons, so if this is the configuration, this is called fully filled or completely filled. That is, when all orbitals in a subshell contain 2 electrons each. Okay. So, one orbital can contain a maximum of 2 electrons. But why one orbital can contain a maximum of 2 electrons? Why cannot we place 3 electrons in a single orbital? Or why are we writing the electrons in the form of opposite spins, that is one upward and one downward? This was explained by the next rule, that is called the Pauli's exclusion principle. So, the next rule is Pauli's exclusion principle. So, Pauli's exclusion principle said that no 2 electrons in an atom can have the same set of 4 quantum numbers. That is, 2 electrons in an atom can never have all 4 quantum numbers same. At least one quantum number has to be different. At least one quantum number has to be different. So, as a whole, this set, the set of quantum numbers N, L, Ml and Ms, that is principal, azimuthal, magnetic and spin. This set has to be unique for every electron in an atom. Okay. This set has to be unique for every electron in an atom. So, by this rule, now if we take 2p, okay, so minus 1, 0, plus 1. Now, if we place 2 electrons like this, what will happen? For electron 1, n is equal to 2, L equal to 1, Ml equal to minus 1 and Ms equal to plus half, right. Now, for electron 2, n equal to 2, L equal to 1, ml equal to 0 and ms equal to plus half. So, both these electrons have magnetic quantum number different. Now, similarly, if we write like this, so what happens? For electron 1, we have n equal to 2, L equal to 1, ml equal to minus 1, ms equal to plus half, right. Now, for electron 2, n equal to 2, L equal to 1, ml equal to minus 1 since they are both in the same orbital, but ms, that is the spin quantum number for this electron, cannot be plus half again. That is, we cannot write like this. If we write like this, then for this electron also ms will be plus half. So, all 4 quantum numbers are same. This cannot happen. So, we will have to write like this. So, for one of them ms equal to plus half and for another ms will be minus half. So, if we write the all 4 quantum numbers again, then for the second electron in this case ms becomes minus half. So, now all 4 quantum numbers are not same. So, this can exist. Okay. So, this was the Pauli's exclusion principle. Now, why can't we feel more than 2 electrons in an orbital? Because now if there is one more electron and we want to feel them in this orbital, is it possible? Because if we feel another electron, it can be either like this or it can be like this. So, in neither of the cases, this third electron can have a unique set of 4 quantum numbers, because the first 3 quantum numbers are same already and the 2 possible spin quantum numbers are also taken. So, this electron will have similar quantum numbers to at least one of the electrons here. So, 3 electrons in a single orbital is not possible. We will have to put the third electron in some other orbital. So, Pauli's exclusion principle has been discussed. So, we have discussed all the necessary rules that are required to study the electronic configuration. So, now we will start the electronic configuration. So, to write electronic configuration, there are 2 possible ways. One is the orbital method, that is SAPB-DC, writing like this, and another is by the block method, that is diagrams. We can draw like this. So, these are the 2 methods for writing electronic configuration. So, we will study about these 2 possible methods of writing electronic configuration in the next lecture. Thank you.